HVAC 360 is brought to you today by Boiler Room Films presents Radiant Mean. In a world completely glazed over, one man, pushed too far, stands up to shatter the status quo, unleashing massive destruction. Audiences call it a scorching drama, methodical and calculated terror, and a clear classic. Radiant Mean. You'll find yourself screaming for shade. This film is not yet rated by the Passive House Institute and may not be suitable for all designers. Hey, what's up, everybody? Welcome back. This is episode number 95. Matt Nelson here, your host for HVAC 360, helping you go further and faster in the field of HVAC. Listen up to hear stories, interview industry experts, and learn more about HVAC than you can shake a stick at. In addition to this podcast, you can always find more information about HVAC over at HVAC360.com. Get on our mailing list. We're sharing stories all the time. We're playing little games. So if you want to be a part of that growing community, jump on over there now and sign up for the newsletter today. If you like your HVAC with a little extra shot of refrigerant. So, what's up this week? This week, I am concluding my conversation with Robert Bean. Robert is going to, if you haven't visited yet, Robert over at healthyheating.com, that's his website, and he has a lot of information out there. Go take a look at that. He is an industry expert and an icon. Also, one of the co-hosts of the Building Edifice Complex. So I think it's a great podcast, and I think we mentioned it during the show. So if you this one is going to be dedicated specifically towards radiant mean temperatures and what they are and why you should care. And it's something that not everybody really knows about, but you should be very interested if you're going to step up your HVAC game. If you're a designer, you got to know, because this can totally jackpot your design. This can really put a bad mark on your reputation if you end up getting a space that is just out of control, something that you should have known about already. For your contractors out there, if you're trying to solve a problem, a radiant mean problem with more HVAC, you probably want to listen to this because you're probably not going to be successful. This is not something that you can just throw more cooling at. So without further ado, we're going to cut to the tape for this part 2 of our conversation with Robert Bean right after a word from our sponsor.
If you want to have comfortable buildings, you have to, or have people be comfortable in buildings, I should say, because that's the more correct way of looking at it, is you have to do comfort calculations. And what comfort calculations entail is doing an MRT calculation. And the MRT calculations aren't that difficult. I mean, we know what the U values are of the walls. We can calculate that. We know what the outdoor temperatures are. We know what the indoor temperatures are. And through a simple calculation, we can calculate the inside surface temperatures. And then also, through glazing systems, we can either use, Windows, which is a Lawrence Berkeley National Lab software, free software tool, by the way, or you can go to the ASHRAE handbooks and you can go to the tables and, we can calculate the inside surface temperature of that. So once we calculate the inside surface temperatures, from there we can calculate the MRT. Now, for those nerds in your audience, I would suggest at least once in your career, you do a manual MRT calculation. And once you get through that, you will absolutely be depressed that you wasted so much of your valuable life doing that calculation. But you'll be proud of yourself because you made it through the other side. But by doing it manually, you get an appreciation for the complexity. But It's both simple and complex, the calculation, but the software today can do it for us. So the ASHRAE thermal comfort tool has a MRT calculator. The Center for the Built Environment have an online MRT calculator. So it just, you can do the calcs. And the nice thing about it, like, we can take a single room and really, like Matt. Well, I can, because I've been doing it for so long. Usually within 30 to 60 seconds, I can tell whether a room is going to have a problem or not. But to go through and put the inputs into the online tools, really, like, we're talking maybe at most a 20-minute exercise, and you don't have to do all the rooms. All you got to do is just use your judgment and look at a floor plate. You look at the corner offices. You look at the ones that are west, southwest, southeast, that have lots of glass or have some really funky geometries. Those are going to be the zones, what I call the rogue zones, that are going to give you problems. They always give you problems, right? And so you can take take a couple of the worst case zones and do the calculations. And from that, you can identify the architectural problems. And the architectural problems will be too large a window to wall ratio, right? Instead of being something like 35 to 40%, it's like 80 to 90%. So too much glass, too poor quality performance glass, wrong coatings, and over framing the building. So too much structure in the building itself. So get rid of some of the framing materials, put insulation on the outside, get your window area down to something that's more reasonable, and put in high performance glass, and you will solve almost 90% of all the thermal comfort problems that occur in buildings.
Reduce the glass. I know in conversations with some of the glazing manufacturers out there, they're like, "Oh, there's nothing wrong with using a lot of glass," but you just
idiots.
you can't get around it. Think
about this, Matt. Think about this, right? All right, so let's go back 3000 BC. All right. So I want everybody that's listening, we're going to get on the timeline machine, and we're going to go back 3000 BC, and we're going to build ourselves a rock house. Okay, like the Three Little Pigs. We're going to build the rock house. Okay, so the rock, let's just say it's like an 8-inch or a 10-inch rock. An 8 or 10-inch rock has a U value, or an R, let's say call it R value of something like R3 or R4, if that, maybe 3, maybe 2. Okay. All right, so we've just built a rock house out of an R2 or R3 building material. Now, let's get back in our time machine. Let's come up to 2018 when time of this interview, and let's take a glass building. You know what the R value is? R2 or 3. They're idiots. We can't. The glass people want to sell glass, so use lots of it, right? It's like asking the barber if you need a haircut.
Right. It's really unbelievable, and I think part of the thing you don't necessarily realize if you're not looking at the mean radiant temperature, you're going to have because all the engineers will certainly appreciate the fact that their equipment is jammed into these mechanical rooms, and they're giving no square footage. Period. They no room for maintenance, no room for nothing. Square footage is king. But what do? They coat the building in glass. And what does that last, 5-10 feet? It's unoccupiable because of this mean radiant temperature effect.
Yeah, so let's talk about that, and also, let's put this let's hit the owner's pocketbooks, or the right. So, if you think about this, if we take, I don't know, let's whatever, say 10. Well, let's say the first 6 or 8 feet of a building that can't be occupied, right? Because it's uncomfortable. So I don't know. You got a calculator handy there? Let's make the math simple. Right? Let's take a 10 by 10 room, right? I'm gonna give you some numbers, Matt. We're gonna do some live engineering here on your podcast.
Okay.
Okay. So let's take a 10 by 20 room, right?
Okay.
So 200 square feet, right? Okay, everybody's following along here? Okay, so we've got 200 square feet. Now, let's take a square footage cost to build that room. Like, I don't know, like, here in Calgary, it might be $175 a square foot.
Sure.
Right? So we got 200 times $175. So that's $35,000, right? To build that space. Okay, so let's say, for example, that you could only use, instead of a 20-foot wall, let's say a 20-foot wall is facing south. And the reality is that you can't use 4 linear feet across that. Now let's make it 5, right? So what we're saying there is that 5 feet in front of that 20-foot wall we can't use because it's uncomfortable. That means we've spent $17,500 on a space we can't use.
Yep.
Now, so that's take the 35 grand, and that's add it to the money that we can't occupy, and now that's divide that into the 5 by 20. Like the price per square foot almost doubles. So people need to understand that, and that's just one room in one building.
Right.
So now that's gross this up into the entire building. So if there's lots of rooms like that, that happens all over, right? So now you're spending not $17,000, but maybe it's $170,000 that you've spent on areas that you can't use. Now that's gross it up even further. Let's say that's one building. Let's say it's a house. That's one house in a development that might have thousands of houses. So now you're talking millions and millions of dollars in a development that were spent in spaces that can't be occupied. One development. Now let's take that development and that's gross it up across the continent. Now I hope people are beginning to understand the wastage that occurs in the world of architecture because we build spaces that we can't occupy. It's incredible.
It is. Even from a standpoint of it's very understandable leasing space. If you have built a building on spec and you can't lease the space because it's uncomfortable, nobody wants to lease space that they can't use. So then the entire floor plate, you might have huge vacancy problems in your building. You can't lease it as a landlord. It becomes wasted money essentially.
Yeah, so this is a really interesting topic because in the past, when property developers would put up a building and lease it out, they didn't care, right? Because the people leasing it paid for the utility bills. The people occupying the building might complain, but many of them were afraid to complain because they didn't want to be perceived as a whiner, right? And so people just put up with it, and they would come to work with their own, little plug-in electric heaters, right? And, you take an office building with 20 people with 20 electric heaters, starts to add up, right? Plus it's a fire hazard. And and they would, be wearing clothes, and the productivity would go to all, hell in a handbasket because they were freezing. Well, the property developer could care less, right? It wasn't their issue. It was the people that leased the space. It was their issue. They're paying the bills, and it's their people in the space, and we don't want to hear about it. Now, so along comes some high performance building specifications, right? And now all of a sudden, it's kind of like, I always make the analogy. It would be like living in a village where everybody was riding a jackass, and all of a sudden a thoroughbred shows up into town, and everybody goes, whoa, I didn't know we could get a thoroughbred. And so all of a sudden, everybody gets rid of their donkeys, right, and wants to ride the horse. Well, we now have enough horses, thoroughbreds, buildings out there that people understand that for the longest time we've been occupying jackass buildings, right?
Yeah.
And the problem is that when we build the new thoroughbred, which is great. I mean, it's there's no doubt about it. It's great that we have the wherewithal now to understand what a high performance building is all about. But we still have all of this bad buildings that exist. Now, unlike a back in the old days, we would unfortunately have to, and this is a nice way of saying, put the animal down, right? Right? I remember my sister, she was traveling to Japan and they were staying at this the farm in Japan. And my sister said, yeah, and he caught a deer for dinner.
Wow.
Joanne, you don't catch deer, you kill them. So we've got all of these buildings, but unlike the jackasses and the horses, we can't put them down. We're stuck with them, right? So we've got all of this, and it's a drain on our resources, and so there's nothing sustainable about a bad building because it becomes a drain on our energy system. So yeah, it's good. Okay, we can build a nice new building, but we have our problems still exist that we have to deal with. So yeah, thanks for triggering that emotion, Matt.
Not a problem. I guess the funny thing is in the situations that I've been involved with, where mean radiant temperature has been part of the problem. The engineers just keep going back to load calculations. They don't really address it, and they want to throw more air at it. They want to throw more cooling at it, and it doesn't work. So Robert, obviously you've seen more examples of this than I have. What can you do? I mean, it's not as simple as putting shades on the inside, because that just delays the inevitable. It's just another surface to radiate heat.
North Americans, we're so. I say this with so much love and affection, Matt, but North Americans, we're idiots. We're like, if you go to other parts of the world, right? Let's go to Asia, for example, right? Because they have this all figured out. Like you go to a hot, humid climate in Asia, right? How do they stay comfortable? Well, first, they get the building off the ground, right? They put it on stilts. What a novel concept for places like New Orleans, right? Get the building off the ground, right? Build a great big huge roof so you got shading. Put in great big windows that you can open up so you got natural ventilation. Get half naked and drink lots of beer and you're good to go.
Done. Sold.
Right? Done. Here in North America, we build these buildings without overhangs. We don't put windows that can open up. We think that by putting shades on the inside that we're going to prevent the heat from getting in. No. Once it comes through the glass, it's in the building. Right? And so we've gone to job sites where people say, yeah, but the blind is closed, and just because they can't see it, it's like the moose hiding behind the big tree with the hunter on the other side. Just because he can't see the hunter, he thinks he's safe. Right?
Yeah.
It's like, come on, man, the heat is in the building. The blinds are like at 120 degrees Fahrenheit. They become radiators inside a building that you're trying to cool. It's absolutely stupid. If you want to passively cool a building, you have to keep the shortwave radiation off the building. It's not that complicated, right? So that's why we build overhangs to shade the building. It's why we put shades on the outside, not the inside. The Europeans get it. The Asians get it. The Middle East gets it. What the heck happened here in North America? Like, what happened to our brains? I don't know. Something happened to us here, Matt, when they started to occupy this continent.
It's all in the fashion. You gotta, you're gonna be a little uncomfortable, but you're gonna look good.
It's all about looking good. Yeah. So, but it is changing slowly. We are starting to see changes, but man, it is so frustrating because, and particularly for myself, because the clients that we get tend to be above average intellect, above average income earners. So these aren't stupid people. Like, these are people that have 1-2 degrees, or they've worked really hard to get what they have. So let's take an example. We had a client that we inherited. This individual and his spouse, both university educated, physicians, had a lot of money, a lot of brains. One of them had a plane, was a plane. And so they had the plans came to us, and I'm looking at the plans, and I'm looking at all of the areas that I know is going to be uncomfortable for them, right? And I'm sitting here and I'm talking to him and her, and I'm saying, can you explain to me sort of what you're trying to achieve here with the house? And they go on to this philosophical discussion about, we want it to be healthy for our kids. It's going to be our retirement home, and we want it to be sustainable, blah, blah, blah. And I said, I'm just going to want to ask a couple questions here. That twin engine plane that you got there, just how much research work did you do, before you bought that plane? And the guy went on about, oh man, I spent months and months, looking at it, and then I went and got my pilot's license, and the guy put in an effort, right, to get this plane. I said, well, how much effort did you do to think about your building? And it was none. They put all of their faith in the hands of an architect.
Yeah. Right.
And so why is it that educated, well-off individuals will spend hours and hours doing research work on their plane, on their elective surgery, to buy a boat, whatever. But when it comes to their own home, they will hand over the responsibility of that to somebody that will never have to live in the house.
Yeah.
Right?
Yep.
It's completely bizarre. And so we then said, okay, well, it's time that we have an education. And so we sat down with the tools, we talked to, and because they were physicians, they got the whole human physiology thing right off the bat. Like they're going, oh, yeah, right. I knew that. Yes, you did. Right. But no one talked to them about what happens when you take these human factors and you put them in the inside and you separate the inside from the outside with this enclosure, and you talk about the flaws, right? They didn't. And once you explain that to them, they just go, wow, this is just so simple, and this is so practical, and this makes so much sense. And I go, I know, I wish I could talk to people like you all the time before you talk to your architect.
Right. Yeah, I think a lot of people, even if you have a good architect, a good engineer, you can get a building that functionally works. It doesn't leak. It works well, but it's still, like you said, it violates some of the thermal comfort, noise comfort, these different comfort aspects. You could have a building that's completely fine but is unusable. It's Yeah. So that's why, when we talk about the term indoor environmental quality, it's, we have to understand that these are integrated principles. And so the human is the ultimate integrator, right? The brain ultimately integrates everything that it experiences in a space. Mm-hmm. And so if we want competent architects and we want competent engineers, and let's not forget about the interior designers, because they play a huge, huge role in this as well. And I want to differentiate between an interior decorator and an interior designer, completely two different professions, right? So the interior designer, 4-year degree program, 4 years of ArtiClean, has a code of ethics. They're in the same playing field as the engineers and the architects, right? If we want these people to be competent in their practice, we have to get them to understand human physiology and psychology, even at a really basic level, right? So that their approach to design can actually start with the occupant and work outwards rather than starting with the outside and working in. And one of the very first things we need to do is teach clients, the people that are paying the bill, to turn off their visual stimulation and then write a specification for sound, write a specification for odor, write a specification for the thermal environment, write a specification for vibration, write a specification for the indoor air quality. And once you've written the specification for those elements, then you open up your eyes and say, okay, now let's deal with the geometry, the aesthetics, the form of the building, but not until you address those other 5 metrics. Yeah, and I think that everybody, as a architect, engineer, even from an owner, everybody wants it to be easy. Everybody wants to, they like the prescriptive approach to designing a building and doing that. That's really, and then when you think about, hey, Mr. Owner, think about these things, and they really don't necessarily know how to put them all in verbiage that's really relevant. That'll key in to the designer's plans.
Yeah. So one of the things that we do with our clients is we have them tell us what they don't want in the building. And then we have them hold us and our design team accountable to that. So so think about that. Most people say, this is what I want in the building. Right?
Yeah.
What they're missing is what they don't want in the building. And that is actually what needs to have happen. So if you don't want noise pollution, if you don't want, aromas from your neighbor's unit, right? Smoking or cooking, like in a high-rise multifamily building, right? If you don't want to have to put on your snowmobile suit in the wintertime, right? What don't you want is more valuable than what you do want.
Yeah.
And the nice thing about that is that people get that. People can do that. And so and this is another danger that we see oftentimes, particularly with professionals, where they want to get involved in the design of the building. Rather than specifying what they don't want, they'll start to actually get engaged with the design process. And we tell them, like the client, the more you get engaged, the more you're going to have to be responsible for your decision making. But if you tell us what you don't want, then you've already set the specification and you can hold us accountable to that. So that when you move into the building, if you've got to put on your snowmobile suit, then we've failed. If you can smell your neighbors, cooking in the next door, then we've failed. If you can hear all of the noise problems outside in the street, then we've failed. Because you said to us in our contract discussions, this is what I don't want. And now I've got it in my building. You're bad, not me.
Right.
Right. And that's a real twist on things, and it makes people uncomfortable. Makes design professionals uncomfortable. But that's why we're engineers, and that's why we're architects, and that's why we're interior designs, because we're supposed to know this stuff, right? We can't keep putting up buildings and it's like a crapshoot, okay, well, we're going to spend whatever, take a custom home, right? Whatever, say it's $4 million. We got to stop gambling with people's money.
Yeah.
We know this stuff. It's called science. Right?
Yep.
It's fundamental stuff. We know it. Let's apply it. Let's just use the stuff that we were taught, right?
Absolutely. No. So I guess that's the whole thing, and just being able to understand and educate the owner as to what they don't want in a house. And
yeah, I mean, here's another example, right? So, and what you can do, and for those people that are building houses now, if they're listening to the podcast, and sit down in a room with your eyes closed and a piece of paper, and let your other senses get engaged, and write down the things that you don't want to hear. We've had people come back to us and say, you know what? I was in my living room. My kids flushed the toilet. I heard the water running down the wall, in the pipe that was in the wall separating the living room from the bathroom. I don't want to hear that again. I get that, right? Who wants to hear that, right? Who wants to be entertaining people? You're at a dining room table. There's 5 or 6 of you around, and someone goes to use the washing facilities, and you can hear the water running down the toilet pipe, the drainage pipe. Come on, who wants that? We don't have to have that kind of stuff. We can engineer it out, right?
Right, and I think part of the key aspect of this like you said in the beginning, challenge the architect, challenge the engineer to design a building that really suits you. And I guess the critical thing is do this thinking ahead of time. If you're the owner, the cheapest way that you can design your building or get it built is by setting these goals and anticipations early in the in the design phase. So you're not re-engineering things, you're not redesigning things, relaying out things. That's part. Any architect engineer will understand that. Really, owner changes. Really kill the whole design flow. They gotta restart things, and that adds mistakes to the project.
You're absolutely right, Matt. You're bang on. And just to give you an example, we had a project, custom home again, where we had worked for almost a year with the client to get the enclosure right. And part of that was to get the right window to wall ratio, get all the shading right, helping them pick all of their interior finishes for, low VOC content, blah, blah, blah. And then also to reduce the thermal bridging so that we had really good MRTs in the winter and the summertime. So part of that was to have exterior insulation on the outside, right? That's why they call it exterior insulation. And so I happened to go out for a site inspection. It was, and I get out there, and the window installers are putting the windows in, and there's no exterior insulation on the outside of the building. And I'm going, whoa, guys, aren't we missing something here? There's supposed to be exterior insulation, 2 inches of rigid insulation on the outside of this building. You guys are popping in the windows. Like you're way ahead of the game here. And they go, no, the owner decided not to put the exterior insulation on.
Ooh.
And I said, what? Hang on a second. So I get on the phone with the client. Sure enough, he said, yeah, we decided not to do it. And I just said, okay, well, let me explain what just happened. So in the original design, with the exterior insulation, everything that we had done, we got the loads in the building down really low, like less than 15 BTUs per hour per square foot, which is really good for our climate zone, right? Mm-hmm. And because the house was heated with the underfloor heating systems, we were able to simplify the entire design. We had one boiler, one pump, multiple zones, all running at the same temperature, which was adjusted up and down based on outdoor temperatures. It was the most simplest, elegant, lowest cost mechanical solution that we had for that project. By eliminating the exterior insulation, all of a sudden the loads doubled. And because the loads doubled, now we had this convoluted temperature profile within the space at design conditions. So we needed to put in mixing valves. We ended up with 3 or 4 mixing stations. So now, but some people might not understand what that means. What it means is that instead of having one homogeneous temperature for the building, now we had 4 temperatures, and that means 4 different control systems. Every time you add a control system onto a mechanical, you may as well add another $1,200, $1,400 onto the job site, right? So now we've added more complexity, more cost, more load. The boiler size had to go up, and now for the life of this building, you're going to pay more for utility costs. You've induced more complexity, which means more things are going to break down. Now you've induced more maintenance costs, and the list goes on. One decision.
Right. Yeah.
Right. The owner made. And of course, then from our perspective, it required a redesign. So he had to pay us twice for our engineering fees.
Eek. And it just boggles my mind. I'm like, when you're at that stage, exterior insulation, the rigid 2-inch rigid. What are you thinking? It's not, it's free energy after the fact.
Yeah. So, shame on me and shame on our firm, because obviously we didn't ingrain in our client how important this is. We went through the exercise, but ultimately he made a decision without us, and that had a huge impact. So He's not 100% to blame. We're also to blame because obviously we failed to communicate just what that meant ahead of time, right? So, yeah, lesson learned. That's why we have our website. So we can pass that kind of information on to people. It costs us a lot of headaches. It costs the client money for the redesign, obviously, and it's obviously he's gonna pay for the rest of his life as long as he owns that building for that energy load. But for us, it's frustrating because when we think we have it solved, something will happen, and then we learn from that, and then we put it on the website.
Right. And I think it's important for people out there to understand. It's when I think of passive house, when I think of these low energy buildings, you think of smaller and smaller mechanical systems, and you'd kind of think that at some point it would go to zero, that it would you wouldn't need it at all. But I think that what you end up with, if you have a very good system, you've engineered, you've been paid for your time to engineer it properly. You have a simple system that's not going to break down, that's going to be very usable to the end user. It's simple to understand, and I think you get a lot of advantages without spending hundreds of thousands of dollars on mechanical system components that you shouldn't necessarily need. Just if you've put a little bit more thought.
Yeah, and and in all fairness, like there are some really good passive house designers that are out there in North America, and some of our good friends of mine. And you're right. When you get a good passive house design, it simplifies everything. The loads are micro loads. The equipment is small, basic, simple stuff. Doesn't need to be complex. And that's the beauty of the passive house. There's one of my favorite engineers in North America is Jeff McDonald, and he talks about the enclosure is the first solution to heating, ventilation, and air conditioning, right? So even before you start talking about pumps and fans and boilers and heat pumps and chillers, blah, 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 let's talk about the enclosure. And that's what the passive house is all about. It's, we can solve a lot of thermal problems with dumb stuff like better windows, better insulation, reduced thermal bridging, right? And the nice thing about these things is that they don't need, and I put this in parentheses, maintenance, but insulation doesn't need to be maintained. Caulking doesn't need to be maintained, sort of. Good windows don't really need to be maintained. Like they're going to last a long, long time. But when you solve thermal problems with mechanical solutions, it's like putting, somebody that's going to need therapy into your home for the rest of its life. Because what happens is that when you got a bad building, one that's built to code, by the way, that you put in this mechanical system, and of course the building gets commissioned, the mechanical system gets commissioned. Shortly thereafter, the clients start to complain about overheating, underheating, drafts, noise, odors, sounds, this kinds of stuff. And so you bring in the first therapist, right, who's the first contractor to come back. He does what he can to tweak the system. He says, there's nothing more I can do. Here's my bill. Have a nice day, right? But then after a year or more of putting up with that crap, the owner gets fed up. He says, well, there's no point calling back the first guy because he did dick. So let's bring back a new guy. So now you got a new therapist, right? So the new therapist, he's got all these new ideas about the system. So he starts to tweak this, that, and the other thing, tries to get it to be a little bit better, says to the owner, here's my bill, pay it, have a nice day, right? Well, then shortly after, the next year, the owner discovers that really the first guy and the second guy didn't fix it either. So he brings in a third guy. So now you got three therapists. And so you know where I'm going with this, right? Is that after 20 years in the building is so screwed up because it's had multiple therapists in there trying to fix it. And the reality is that you could have prevented all of that by just simply building a really good building in the first place and put in dumb controls. Yeah, Matt, I'm going to go on another tangent here. Are you ready?
All right, fire away.
Let's talk about the Internet of Things. Okay. So we have a number of manufacturers who want to try to get consumers' money for zippy stuff, what I call zippy high-tech stuff, right? Smart thermostats, right? Here's a news flash for people. Smart thermostats will not fix a bad building, right? And so we've got people selling, the connected fridge, the connected television, the communication system is connected, the HVAC is connected. And by the time they've spent all of this money on all of this interconnectivity, what they've got is a connected piece of crap. And what they needed to do was to take the money that they were going to spend on the high tech stuff and build a better building.
Yeah.
Don't spend $300 on a smart control that's not going to do anything when you can take that $300 and put it into, let's say, a MERV 14 filter or 13 filter, right? Instead of putting in ducts that are screaming at, 800 feet per minute, upsize your ducts and get them down to 500 feet per minute. Put in the better filter. Spend the money where it's supposed to be spent. Get the building fixed first. Forget about the technology. The technology you can have after you get the building stuff solved. Now, having said that, okay, one of the things that the technology does do is it provides data. The data is more valuable than the service of the device. So when we have these high-tech devices in a building, it does tell us how the building is performing, how people are operating. So from that perspective, yeah, okay. But don't sacrifice the building so that you can buy zippy stuff. That's
Right.
my message.
That's fantastic. But the only problem is it's only the nerds like us out there that will be interested in the sensory aspect of it. They're not it's the typical homeowner doesn't really care about the data and the trending, and not unless it's made dirt simple and they can have some sort of actionable recourse to it.
Yeah. I was just telling you earlier that I was down in Houston for the ASHRAE AGM. Right. That's for those that may not know what ASHRAE is. The old description, that's the American Society of Heating, Refrigeration, Air Conditioning Engineers. Anyways, worldwide organization. We have something like 56,000 members. We get together twice a year. This year was down in Houston. I sat in on a really good presentation by Dr. Zoltan Nagy through the University of Texas, Austin. And he was doing a presentation on Bluetooth technology. And through the use of Bluetooth technology, they were able to reduce the chilled water consumption in their engineering facility by 8%. Now, the Bluetooth technology cost them nothing. I think it was under $20 or $30. But by monitoring the data using the Bluetooth technology, they were able to change how the system operated, their HVAC system operated. And to be able to reduce chilled water consumption or chilled water use in a building by 8%, that's a big deal.
Yeah. Especially in an area like Houston where it's, it was probably nice and toasty when you were down there for the show.
Well, yeah. So if you think about it, right? So, there was, I don't know what the lines, because they have a central plant there at U of T Austin, whether there were a 6 or 8 inch chilled water line, maybe even bigger serving that building. Right. So that energy, needs to get pulled. The heat needs to get pulled out of the building, goes back to the cooling plant. Right. So you're talking about pump power. You're talking about fan power. You're talking about all of the maintenance on the water system, all the control valves, all the dampers. If you can reduce chilled water by 8% into a building like that, it's the real deal. Those are real numbers. Right. And with a low cost Bluetooth device. So, okay. I'm sold. Put me in, coach. I'm ready to play. I get it, right? But if you're going to spend $250 or $300 on a smart thermostat that isn't going to fix the mean radiant temperature problems, fix the mean radiant temperature first. The thermostat's not going to do dick squat for you.
Right. Yeah, and I think as a general rule, you're looking at engineers. Hey, there is that trade off between the building enclosure and your the size of your plant. And I think that you should be looking at instead of, newer technology. You should be getting in and learning the building enclosure on and how to improve that to simplify your systems, because going forward, that's going to be where the value is to an owner, to be able to demonstrate that, hey, I've been able to, work with an architect, because, the architects, they really don't understand the building science aspect of it a lot of times. They really they want to. There's some of them that do, but in essence, you can take ownership of that as a HVAC designer and really kind of increase your value to your clients, to be able to kind of understand what this is and how to treat it, and how that really translates into the design.
Yeah. And so you bring up a really good point. And what's interesting here is that when you look at the U.S. compared to Canada, the U.S. is really adopting this. Like, I see practitioners from all over the country when we go across and we do our talks, where the mechanical practitioner is really starting to jump into the building science part of it. Or we're seeing building science firms, bring in mechanical engineers into their fold so that they can deal with both. Now, in Canada, for some weird reason, I don't understand this, at the commercial level, the engineers get it, but at the residential level, there's like the residential HVAC contractor just like is putting his hands over his ears and his eyes and his mouth. See no evil, hear no evil, talk no evil. Well, just substitute the word evil with building science. I don't want to see the building science. I don't want to hear the building science. I don't want to talk about building science. I'm just HVAC. Right? It's bizarre. And that needs to change. So for the Canadians listening to this broadcast, particularly the associations, the Heat, Refrigeration, Air Conditioning Institute of Canada, the Canadian Institute of Plumbing and Heating, these members need to start to understand buildings besides their own, expertise in mechanical systems. It's really important.
Right. Rarely are you going to, if something's too hot or too cold, it's not going to be, the first call is not going to be to the architect to say, hey, this building is uncomfortable. It's going to be to the HVAC contractors. It's going to be to the engineer. Hey, what's wrong with this building?
Yes, exactly. Yeah, and you made a very valid point, is that when you begin to take on this knowledge and take responsibility for that, you become a much more well-rounded practitioner, and you can charge for that.
Absolutely.
I built a business around it, right?
Yep. So I guess if people want to reach out and connect with you, how would they go about? What's the best way to do that?
I'm trying to hide, Matt. Okay, so listen, if they want to engage in a dialogue with me, use Twitter. Why? Because you only get 126 letters and I only get 126 letters. We can have a really short conversation, right?
Yeah.
Right. If you want a long conversation with me about fundamentals and principles, use our LinkedIn discussion group, right?
And where would that be at?
So they can just Google, was it Robert Bean, RET, LinkedIn, something like that? That'll take you to. There's also a link on our webpage. Contact us. It'll take you to the LinkedIn discussion group. Okay. If you want to talk about music and guitars, you can catch me on Facebook. Right. And I have to say that, if you want to call me about your problems, I've made a business out of listening to people's problems, but we charge for that. Right. So
no free consultations.
No free consultations. Right. But, so like Twitter, nice little burbs. I'm happy to tweet with you. If you want to take a little bit more on the principles and fundamentals, I'm happy to talk to you on LinkedIn. Anything beyond that, get your checkbook out.
Or catch you at one of your seminars.
Come to the seminars, come to the conferences. I'm always happy to talk to people there about their problems because I've been paid. But that's that's a lesson for everybody that's listening, right? We don't do stuff for free, right? Otherwise, we'd not be able to. If we did stuff for free, we wouldn't have our website to share all the mistakes that we've made.
Yeah. Right.
Right. That's how stuff happens. We live in a capitalistic society, right? So when it comes to consultations, then you pay for the good guys, and I pay for consultants. I mean, we come across some projects where I don't know what the architect was on, but the geometry is so funky that we'll call guys like Peter Simmons up. We'll just say, you know what, this job is like so twisted that we need your help. So we pay for consultants too.
Perfect. All right. Yeah. Well, Robert, I appreciate your time and your wisdom, and thanks for being on the show.
Matt, it's always a pleasure, man. Always great talking with you.
All right. Thanks again to Robert Bean for taking the time to chat with us. Check out show notes. This time it's going to be at HVAC360.com/95. That's it for this week. Hope this was helpful. It was a real eye opener when I started getting into this and discovering this. So I hope you can take away the same thing. This is definitely something that should be shareable to a number of people. Robert does a great job of explaining what radiant mean temperature is. And as I mentioned at the top of the show, if you want to keep connected to this community, this growing community of HVAC enthusiasts, you can go to HVAC360.com and sign up for our mailing list. Also, if you can do a second thing just to get more people interested and this exposed to more people in HVAC, if you could go ahead and give us a rating in iTunes, that certainly helps. That's certainly the kind of a benchmark. A rating and review would be much appreciated. And I'll give you a shout out if you're one of those people who actually take the time and go and do that. I deeply appreciate it. Well, thanks so much for listening. That's a wrap for this episode of HVAC 360. I'm Matt Nelson, helping you go further and faster in the field of HVAC. And as always, know what you build and share what you know.